Right, so I'm GraemeMarlton, and I'm a PhD student at the University of Reading, and my PhD is basically detecting turbulence with weather balloons. And so basically I'm going to talk to you about kind of the motivations for this project, and then how we managed to measure turbulence with weather balloons, some kind of comparisons we did with other turbulence observation methods, and then I'm going to talk about some of the other things we fly on balloons as well at Reading. So I guess probably first thing to start off is, what is turbulence? And I imagine most of you probably experienced turbulence while flying on the plane, and that's the turbulence I'm interested in studying. So turbulence occurs when you have a large eddy or a wave in the atmosphere, and then it breaks down, causing smaller perturbations, and that's what causes turbulence. So main sources of turbulence is the Jetstream. Mountains cause turbulence as air is pushed up over them, and also inside large thunderclouds or heavy rain or frontal clouds, you get a lot of updrafts and downdrafts, and that also causes turbulence. And in the very, very intense thunderstorms, you actually get turbulence outside the thundercloud. It's that the updraft's so strong. So what are the costs of aircraft turbulence? Kind of another motivation of why we need to do it. So atmospheric turbulence causes about $150 to $500 million worth of damage to the airline industry each year. And it can be things like such a stream of losing an engine and all the problems associated with an engine falling off an aircraft. But the main cause for the main cause in turbulence is flying through turbulence costs more fuel because you've got to keep the aircraft on course. And basically, you get the air hostess people going up to go to the loo, and turbulence can't be detected by the aircraft in front. So the first thing you know you're in extreme turbulence is when you're flying through it. And by that point, you're on the ceiling, not in your seat. And this is what happened on a Singapore airline flight to London a few years ago. They were doing dinner service. Dinner's now on the floor. Everyone's bolted in. This guy's still hungry. It's not good. It's not good. So this is one of the other things we're going to hope to make some observations of turbulence, feed it back into weather forecast models, and hopefully improve our prediction of turbulence. So what are the existing methods of detecting turbulence? Well, there's a few. First of all, we've got things like surface instruments and boundary layer Lidars, which are basically lasers which can profile velocities in the atmosphere, and I'll come back to that a bit later. But as you can see, a bit lacking in the height department, can't really detect any turbulence up at cruising altitudes. Then we have cloud radars. They're great at detecting turbulence, although you have to have a cloud for the turbulence to be in. If there's no cloud, no luck. The next thing is wind profilers. They're actually called MSD radars, but I'll just call them wind profilers now. Brilliant vertical range, 2 to 20 kilometers, easily covers the cruising altitude of jetliners. Problem is only 2 in the UK, so a bit sparse coverage. Another source of pilot reports, another source of turbulence observations is pilot reports. So as the aircraft flies through the turbulence, it goes, oh, blimey, that was quite intense turbulence, sends a message to air traffic control reroutes all the aircraft around it. So when that happens, you're limiting yourself to one observation of turbulence. And then after that, you've got pilots. You may have a pilot that had 10 hours experience and goes, Christ, that's the worst turbulence I've ever flown in. I'm not flying again. And then you get a really experienced pilot and go, that was nothing. So there's some subjectivity there. If you've noticed, there's been this rather lonely-looking balloon kind of flying up through the image. And as you can see, it kind of flies through the cloud. It flies through all the clear air turbulence. Brilliant vertical range, so potential to use the balloon as a platform for making observations of turbulence. So how is a weather balloon affected by turbulence? So a few people have mentioned some pendulum swinging effects. So basically, if we think of the balloon and the payload underneath as a pendulum with a moving pivot, when the balloon's agitated around by the turbulence, it causes the payload below to swing. Larger accelerations on the balloon due to turbulence cause bigger swings in the package underneath. So that's great, we could measure it. So what I'm going to talk about is the standard payload that's carried on operational weather balloons that are used around the world by thousands of meteorological organisations. We call it a radiosonde. It comes from the French for the fact the data's transmitted by radio, and the French are making a sounding of the atmosphere, and they've been around since about 1927, and they've obviously just been updated to reflect technological developments of the time. So this one here is a Vaisala RS-92 radiosonde. At the minute, it's the leading market radiosonde until Vaisala bring out their next generation one. And it measures pressure using an aneroid pressure capsule. It's got capacitive thermometer up there to measure temperature. It can derive wind speeds from the GPS antenna. And it's got 2 humidity sensors. So one of the problems you have with humidity sensors when you send them up through clouds is one freezes over. So there's 2, you heat one and take readings off the other, and then after 30 seconds you flip them over so you can maintain a good humidity measurement. It's got a 9-volt power supply from, boringly enough, 6 AA batteries, and they're encased in a water jacket. So as you go up into the cold things, the water freezes and it provides a little bit of extra heat for the batteries to keep the current output up. There's a radio link. It's on the 400 megahertz range. Telemeters the meteorological information back to ground, to a ground station, and it will transmit it every 1 second. So using a standard ascent rate, you get about meteorological information every 5 meters in the atmosphere. However, it can't measure its swing. But what they did do at Vaisala was they put a port on the bottom, which meant you could plug other stuff in. And so I'm going to talk about how we exploited that at the University of Reading. So they developed a system which basically can have extra data channels plugged into it. They put it in a box, and then someone worked really hard creating this acronym, which is Programmable Analog and Digital Radiosonde Accessory, Pandora, and we put it in a box. So that was our little joke for science. And as you see here, we've got the standard radiosonde on top. That big white slab in the middle, that's where the batteries sit. And this box underneath is where the data acquisition system goes. I know, you've been telling me for months. So I might just have to. Here we go, right. So the great thing about this is, because I've actually called this an ozone port, so when you hear about, oh, there's a hole in the ozone layer, there are actually these large ozone sensors they put on to actually find out how much of a hole there is or whether there's a hole or not. But obviously that's like quite dangerous, lots of chemicals, and you have to make sure they're upright and things. So, but there's data, there's bandwidth in the radio transmission for that ozone data to go in. Instead of sending the ozone data, we send back the additional channel data. Great thing is, no additional hardware needed. You just click a button on the sounding software, and it'll output all the files. And then we use this, which is called the Pandora extractor, which basically concatenates them all back together, so you can have meteorological data alongside your extra sensor data. So we've got a measurement system. So how do we measure the motion of a weather balloon? So here's another night in my house, playing Wii. And inside Nintendo Wii controllers, you've got accelerometers, which are basically the main motion control thing. I don't know why there's... Yep. So basically, we look at what that accelerometer, which is one of these. I'll put a 5p coin just to give you an idea of the size. So basically, just taking that accelerometer. Don't worry, I've not gutted like thousands of Nintendo Wii controllers. I brought the accelerometer separately. And the one we use is the ADXL325. I think it's done by Analog Devices. It's got plus 5G minimal range, which means they're all set to do between plus or minus 5G in 3 axis, but they can do more. It's just a minimal specification. So we then add some electronics. We've got to design a board, because we made about 100 of these. So we put things like power regulator on, capacitors to modulate the output of the accelerometer. And then we, pop it into a box, tie it to the side of the radiosonde, and we're ready for launch. So there's a 3-axis accelerometer in it, and one of the kind of pre-flight tests we did was which axis gives you the best response to turbulence. So it's a very crude experiment. I erected a big mast on the field site, tied it to it, and just sat there throwing it while I was logging the data. As you see here, the z-axis of the best response to turbulence. So that's the one we're going to be using for our turbulence measurements. So I've just presented a little case study. So these 2 panels here are the standard meteorological data we get out of a radiosonde. Black line there is temperature. The slightly faded grey line's humidity. So one thing we can notice here, cloud, and then we've got Jetstream, but you wouldn't know whether there was turbulence involved. So if we add our turbulence sensor, we can see that through the cloud we're detecting between kind of 2 to 3G, and when we hit the Jetstream, which was probably one of the strongest we've flown into at about 180 miles an hour, 4 or 5G, and if we notice that's around 8 to 10 kilometers, that's the cruising level of your aircraft. So it's probably something you should be worrying about. So we've done this, and we've done about 50 ascents, and I've just plotted a little histogram showing you all the data from 50 cents. So we've done them from Huhtala in Finland, we've done them from Aberystwyth in Wales, and some from Reading. So if you're down to 5G, we know that's good, but there have been times where it's recorded this amount of data and we've looked at it, it's not errors in the radio link, it's, I imagine, the little mass that's inside the accelerometer is kind of leaning up against the side of the wall at this point. So just to give you some ideas of what that G is, at 5G, if you're accelerated upwards at 5G, you won't remember it, you black out. So it's all very well. I've got this sensor I put on the side and I go to the Met Office. I measured turbulence at 5G, and they're like, what are you on about? So what we need to do is need to compare it with other existing methods of turbulence observation and try and have a comparison of what our measurements mean in terms of other things. So I'm going to talk about two. One's a comparison with a Lidar that we've got at the university, and the other is a comparison with the wind profiler at Aberystwyth. So I'm just going to explain about this because I mentioned it a few times, but the best way of measuring turbulence the meteorology community has come up with is a thing called eddy dissipation rate. And so if you imagine we've got a large eddy to begin with, and that dissipates down to smaller eddies and so on, it's basically the rate at which these eddies go from large ones, they pretty much dissipate due to the molecular properties of the air. And so we can use that as a measure of turbulence. So our first comparison was with the boundary layer Lidar. Basically, you can calculate eddy dissipation rate by looking at the velocity variance you detect in the laser beam. Now, the laser beam can detect velocities because in the boundary layer, you've got pollutants and aerosols and other kind of very small particles, and it basically uses them as a tracer to work out the wind speed. And so every 60 seconds, you can get an eddy dissipation rate value. The only other thing is you've got to put length scales in. So obviously, your kind of largest length scale is the kind of total dwell time, if you want, of the Lidar over at 60 seconds. And its shortest length is kind of the difference between like a consecutive reading. So once you compile all that, you can get an eddy dissipation rate. So we did 13 launches. And I say when this was online, because I did some launches, went in to get the data. And this guy goes, I've taken the power supply box. And I'm just like, you've only got one. How? Anyway, so that's why we only got 13 out of what could have been a much potential about 25. And so this is the result. So a nice linear relationship, and we're like, that's great. That doesn't normally happen in science. I'll take that. There's obviously some scatter because the balloon will drift away when you launch it, as you'll well know. We had to do some spatial averaging of the sonde data and the Lidar data. And also we said, well, for the Lidar, let's take half an hour around launch time to smooth out any inhomogeneities. So that's great, but we only really got to like 1 kilometre height because, believe it or not, the boundary layer in this country, especially in spring, autumn, rarely gets above 1 kilometre, and so it's kind of a very small section of the atmosphere to do. So thought we'd get something a bit bigger. So this is the mesospheric, stratospheric, and tropospheric radar at Aberystwyth, and it's the UK's most powerful wind profiler. Operates at 46.5 megahertz. It basically consists of 400 Yagi arrays pointing upwards in a grid. It's got a vertical range of 2 to 20 kilometers, but in the summer months, you can even go into the mesosphere with it. But the most important thing is it can measure turbulence. So I'm in an R-ing. I finally decided we were going to drive to Aberystwyth and do some flights. And so we did 18 flights in the end. We've battled through snow and loads of other stuff to get to this radar site that's in the middle of a valley. Obviously, what we're doing with the MST radar is a lot bigger version of what you're doing with the Lidar. So obviously we have to increase spatial averaging windows, and we increased the time window to an hour. But we got a good relationship. There's a lot of scatter because sometimes the balloon could be 60 or 70 kilometers down the road, but you're also sampling a large part of the Jetstream where you could guarantee the turbulence would be pretty similar. So we're pretty pleased with that. And this is actually ongoing work, hence it's not in eddy dissipation rate yet. The reason it isn't in that is because no one's actually done this before. So it's kind of going out on a bit of a limb, working with what people have found have worked before. So that's basically what I've got to say about the turbulence side of things, but we're not just limited to measuring turbulence at Reading, we have a range. And so the Pandora system, it's just got 4 channels, which means you can literally attach any sensor you want and it will relay it back over the radiosonde. The Pandora board also has things like, it's got a power supply circuit, so you can get 16 volt, 8 volt, -8, a whole range of voltage rails. So I'm just going to talk a little bit about what each one does in the range. By the way, it's not an extensive guide. There are much more than this, but I could go on for hours. So one that I was talking about was the relative humidity sensor. Now, despite Vaisala spending lots of money developing it, it's actually got a pretty slow response. So if you come through a very defined cloud edge, I noticed some of you were showing some videos of kind of going through quite kind of stratiform clouds, and then sometimes you're going through a big cumulus cloud where you're not really sure where the cloud edge was. What we've done is we've attached a photodiode to the top, and basically, as it goes up through the cloud, the sun's radiation coming down is diffused by the cloud, and so you get a very flat line signal. And as soon as you approach the top of the cloud, it starts rising. And when you break out the top of the cloud, because the radiosonde's swinging, you get like a line between a kind of direct beam and a diffuse beam. And so from that, we can work out very interesting properties about cloud layers. So for here, we think there's one big one here, and then there's a very thin layer above, and the relative humidity's struggling to keep up. And so it's a great window. And I'm just going to apologize for some very slow animation. There's another one as well. So here's like a zoomed in view of the top of that cloud. And as you can see, this is where we know the top of the cloud is from the optical sensors. And here's the relative humidity struggling to keep up. So it's actually been really helping finding kind of very thin cloud layers. But then I suppose, what happens if it's dark? So what they came up with was an active method of sensing cloud. And so this is it bolted to a post on a kind of slightly foggy night, 1 November. And basically, what is it? It's an LED source, and it fires a modulated LED source out using ultra-high bright LEDs. And basically, it fires at the droplets. You get a backscatter back. From that information, you can work out things like what your visibility is. And if you've got a few other values, you can start working out the microphysics of clouds. And I mean, they've been trying to attempt this over about 10 years, and one of the problems is LEDs were first all expensive and not that bright, but now they're starting to become very bright, very cheap, and very low power consumption. And so these actually now give you migraines if you look at them, they're that bright. So what we did was a combined flight where we had both the passive and the active sensor. As you can see here, that grey faint line is the photodiode, and as it goes up, you can see this is the top of the cloud, and it's got some variability after that. But the active one says, no, we're not in cloud, and here we are now in cloud. And basically, it sits at a default rail as saying, oh, it can see a kilometre, and then for when it's going through the cloud, it says, right, I can only see 60 metres in a cloud, and we've calibrated against visibility sensors as well. So that's clouds. Another thing that's been mentioned is space weather. So there's a region of the atmosphere about 25 kilometres up where the density drops off enough that ions can be generated, but it's not too high for there to be a lack of stuff to turn into ions. And so a balloon makes a perfectly brilliant sensing platform because you've got the height, you've got your pressure, you've got your temperature, you've got your location, so you've got this wealth of data to add to it. And so how you measure space weather is basically counting. You can use the amount of galactic cosmic rays coming in as a proxy for like your ionization rate. So obviously when the sun's kicking off with its solar storm, this changes the amount of cosmic rays you're getting, and so you can compare things. And there's also variability across the Earth's surface. So it basically works, there's 2 Geiger tubes. Now Geiger tubes run off about 500 volts, so one of the major obstacles was getting 500 volts off a 9-volt battery. And so it was a voltage step ladder device. I'm not too keen on the details, so please don't quiz me. And this is what the finished product looks like. Them 2 black tubes at the end of the Geiger tubes. That big rack of capacitors, the voltage step, because it also relies on looking at each Geiger tube. We've had to write some additional PIC programs before it interfaces to the Pandora system. It's one of the heaviest things we fly at 39 grams, but as you know, 39 grams is quite heavy. So, and here's just a picture of it prepared for takeoff. And so what was done, we've got quite close ties with the Icelandic Met Service, and they said we'll launch one from Iceland, which is a higher latitude, and so the Earth's magnetic field perturbs the measurements you get. And from here we can see we've got more ionisation at Reykjavik than we have at Reading. And so we often launch these during space weather events. You know, people hear, oh, there's a large solar storm, one of these might go up. And we also sometimes do synchronous soundings with a place in Russia as well, who's got like a 60-year record of doing it like every Wednesday or something, which is quite impressive. So, conclusions. So yes, you can measure turbulence with an adaptive weather balloon. The accelerometer is showing quite good agreement with two independent methods. And actually having the vertical profiles of the weather data alongside your measurements is a massive, it's just great, because when an aircraft flies through turbulence, you only get the weather at that level. And so when you get the full profile, it adds to the understanding. And so kind of the next bit of my PhD project is feeding all this information into a model, which is dull, so I've not talked about it. So this will increase our understanding of turbulence, and the adapted sonde system can make measurements of space weather, optical properties of clouds, and we're beginning to go into atmospheric electricity as well. But yeah, thanks for listening. If you've got any questions, that's cool.
On your LED detection of the moisture content for the clouds, are you using visible diodes or UV or infrared?
So we've actually used loads of different combinations. It started off with green because that's something you could see, but we're actually getting to the point now where we might have 4 different LEDs and modulate them, so you can start getting size properties back as well.
There's no single one that gives you better results?
Not that I know of, but there's like popular LEDs. Some LEDs kind of get mothballed as just maybe they're not bright enough or the wrong wavelength, but water's got particular wavelengths in the spectrum that absorb, and it doesn't absorb, so we can use that as a point as well.
How big are your GMs?
How big are the?
Counters?
I don't actually know, because I mean, this is why I said don't quiz me, because it's not my thing. But they're at lengthwise, they're just about that big, so they're quite small. There's like half a cigarette length. I suppose that's probably the best analogy I can think of. They fit into the box. So we've actually fitted the Geiger tubes, the solar radiation sensors, and the accelerometer into a box. And it was a bit kind of almost tight, but everything worked inside it and relayed information. So, yeah.
There's quite a few people who take the data down from the running zones, so they're doing all the other ones around the country.
Okay.
Is the protocol available to actually grab to decode it?
So so this is something we'd like to know, because we don't know what you get, because we have this sounding system that decodes it all, and we don't. It's a black box system, which is one of the nice things about doing this, because we've got our platform. But I mean, it'd be interesting to know what you guys see, and then maybe we could help you. But if it's gobbledygook that Vaisala know how to decode, we might not be able to help you. But if you can pick the values out, we may be able to help you with that.
We'll have a chat afterwards.
Yeah.
Mm-hmm.
What about using laser diode instead of a LED? And you could measure, if you do low angle backscatter, you could measure turbulence and cloud density at the same time.
So a low angled.
Yeah, well, if you used a red, well, it doesn't have to be red, but use a laser diode, and you look at 2 things. Then you look at the level of the backscatter, the intensity, and also you look at the Doppler mixing with the original frequency, and you get the relative movement, but in that would be the turbulence as well.
Mm.
You need a single mode.
Yeah, you need a single mode, which you can do on fibre optic, very low energy as well.
You can do it with the regular laser diodes if you temperature control and current control it.
Yeah.
That's a bit tricky.
But the best thing would be just a telecoms laser diode, which is single mode coming out of fibre, and just have a short length of fibre.
They're very pricey though. I mean, I think it's designed to be a disposable system.
Yeah, so we have never ever, apart from one, never ever got any of them back, and that's how they're designed to be, because when you launch it into a thunderstorm, you're not really bothered about getting it back. And so everything's designed to be low cost in these, which is one of the main reasons to do it. Like the accelerometers cost £1 and the electronics to go around them.
Single mode laser diodes cost hundreds.
Yeah.
Quite a couple even more. Something I was going to suggest along similar lines, why not an ultrasound system? Because that could potentially be lower cost, although the propagation distance is going to be quite low because you get quite heavy attenuation in the air.
So a lot of research has been done using, so as well as having the Lidar profile, they actually did an ultrasound version, and for it to be used in the atmosphere, you need quite a substantial dish, which is getting on to more like an aircraft-based thing.
If you're looking at you're talking about the relationship between the acceleration and the eddy dissipation rate. I'm just wondering if maybe you had some kind of relatively short range velocity measuring system, some kind of ultrasonic backscatter device that operated over short range. I'm not sure if you get the backscatter. I'm just thinking about it right now. Yeah, maybe that wouldn't work.
Okay. Someone had a question in the audience? I don't know. I'm pretty sure someone's put their hand up. But if that's...
I can think of one for myself, actually. I've noticed that balloons rotate. Right?
Yes.
And as a result of that, you get like a coning rotation of the payload dangling underneath it. Doesn't that really contribute to the swinging that you're trying to measure?
So, what we did with the sonde data was we got the raw GPS data out. So it gives you an actual kind of, what they do for the wind data is they smooth it, but with the raw GPS data, you could work out whether it was, kind of almost what the elliptical properties of its swing was.
Right.
Now, in the troposphere, it's normally all right. When it gets into the stratosphere, and we think this may be due to, because you have waves propagating through it causes the balloon to get a spin going. And then, oddly enough, you get to a height and it just shuts off. But we were actually able to, with the accelerometers and the GPS, actually work out pretty well the angle. It is actually a conical swing.
Okay.
And because it's almost in a slightly conserving energy mode doing that, as soon as you hit turbulence, it kicks it out of that. And so we can know that we are definitely in turbulence, but the stratosphere is nowhere near as turbulent as the troposphere. As we found out, it's quite dull, really.
Dull. Okay, any other questions? Brilliant. Okay, thanks very much, Ben.
Okay, thank you.